Hello, so welcome back to video number 2 of section 1.1. Remember last video we had introduced how we can represent systems of equations as matrices and went through a little bit of the intuition on how we might solve a system of equations. And so remember what we can do is we can take, say, a system that looks like this, where maybe in its current state the solution, right? So the values of x1, x2, and x3 that will make this system, that will give me a solution to this system, they might not be clear just by looking at it. Remember, we can sort of manipulate the system in a way that we can come up with an equivalent system of equations that gives us the solution to this one. And so remember, two systems of equations are equivalent if they have the same solution set. And so remember, what we can do to systems like this to obtain equivalent systems is we can add equations to each other, right? So I can add equation 1 plus equation 2 and not change the solution. I can also multiply each of these equations by some constant value and actually not change the solution values. And so what we're going to introduce today is how we can sort of formalize doing this, but with matrices, because it's a little bit easier to work with, as we'll see, with matrices. And we're going to introduce what we call row operations, which will allow us to basically continue to obtain equivalent linear systems and work this system down to something that is easier to solve. So today we're going to introduce the following 3 elementary row operations. And then we will see how we can use them to solve this system. So row operation 1 we'll call, or your book calls, replacement. And so replacement we will think of as adding one row of a matrix, adding a multiple, of one row of a matrix to another, and replacing that row with the new row. We will see, this will make a lot more sense when we see it in an example, but replacing a row with a constant multiple of another row and itself. The second we will call scaling. And so this is just multiplying a row by a constant. And so scaling is exactly what it sounds like. It's multiplying every single element in a row by the same constant value. Lastly, and we haven't seen this one yet, but I think this is the most intuitive as to why this will not change really anything about the system of equations. We can also swap two rows. And so all of these row operations we're going to perform on matrices ultimately, sort of, we can think of them as we can relate them back to what's going on with the system of equations. And so remember, last time we showed that I can, multiply equation 1 by, say, 2, add it to equation 2, and replace that with equation 2, and not change anything about the solution. I also showed, again, that I can multiply or divide any single row by the same constant value. Interchange, well, if I just swapped the order that the equations are given in, it's not going to change the values of anything. So these are the elementary row operations we're going to work with. What we're going to do is we're going to use these on the augmented matrix of this system of equations. And so remember, the augmented matrix, you assign one column for each variable and one row for each equation. And then you lay everything out so that it matches up with where it pops up in the equation. So notice this first column corresponds with all of the entries of x1. The second column corresponds with all the entries of x2. Third column, all the entries of x3. Fourth column, all the entries on the right side of the equals sign. So this is a 3x4 matrix. There are 3 rows, 4 columns. And so I will start to perform the row operations that I would perform in order to solve this equation. And I will start to kind of try to talk about why I'm doing what I'm doing to give some intuition as to how we're going to eventually do this. In section 1.2, we're actually going to introduce a formal algorithm that will sort of always give a roadmap to using row operations to solve a linear system. So the first thing I'm going to do is do -3 times row 1 plus row 3. And I'm going to replace row 3 with whatever I get. So this gives me a matrix where rows 1 and 2 are left completely untouched. And all I'm going to do is now my new row 3 is just going to be -3 row 1 plus my old row 3. So -3 times 1 is -3, plus 3 is 0. -3 times 3 is -9, plus 7 is -2. -5 times, 5 times -3 plus 9 is -6. And 2 times -3 plus 6 is 12. All right, so just for some reference, what we just did is we sort of, quote, created this new system of equations, x1 plus 3x2 plus 5x3 equals -2, x2 plus 4x3 equals -5, and now the new equation that we add equals 12, right? And so this would be the augmented matrix corresponding to this system of equations. And so what we just did is we created a new system that has the exact same solution as this old system. And so as you can see, this new system isn't really any easier quite yet to see the solution to. But maybe if we do another row operation or two, we might be able to uncover the solution a little easier. So next what I'm going to do is I'm going to divide everything in row 3 by 2. This is equivalent to multiplying row 3 by 1/2. And again, everything in rows 1 and 2 will be left completely unaffected. Except every entry in row 3 will be divided by 2. All right. So last thing I want to do is now add row 2 to row 3 and replace that in row 3. And so generally the format I'll use as I'm doing these row operations, I feel like the scalar multiple operations are fairly transparent as to what's going on. If I'm doing a replacement operation like I've done here and here, so each of these are replacement operations. This was a scaling operation. We won't get to see an interchange here, but again, that tends to be the most straightforward one as to what's exactly going on. The replacement operations, I will always put the row that is being replaced last in the sum. So here I was doing -3 row 1 plus row 3, and this implies that I was replacing row 3. And here I'm doing row 2 plus row 3, and again this implies that I'm going to replace row 3. And so that gives me the matrix 1, 3, 5, -2, 0, 1, 4, -5, 0, 1 plus 1 is 0, 4 plus negative 3 is 1, and negative 5 plus 6 is 1. All right, and so now we are at a point where finding the solution to this system of equations is going to be much easier for us. So why is that? Well, let's write out the system of equations that corresponds to this augmented matrix. So notice, by getting rid of the x1 and x2 constants in this last row, by basically sort of using row operations to get zeros in this final row, I found the exact value that x3 has to be. And remember, every time I do a row operation to get a new matrix, each of these matrices corresponds to a linear system that is equivalent to this linear system, or to my original linear system here. So notice here, this set of equations tells me that in my final solution, x3 has to equal 1. Well, if x3 has to equal 1, that implies that x2 plus 4 times 1 has to equal negative 5. And so that implies that x2 has to equal negative 9. And so now that I know the values of x3 and x2, well, that implies that x1 minus 27 plus 5 has to equal negative 2. And so that implies, if I sort of move everything around, that x1 has to equal 20. Right, so 2 plus 27, or negative 2 plus 27 is 25, minus 5 is 20. And so notice, by row reducing a matrix to something like this, where I've got all zeros, 1, 1, and a constant, then I have an equation, this was already given to me, thankfully, where now I've only got 2 variables, and then finally an equation with 3 variables. I was able to just sort of work my way back up and figure out the solution to my linear system. And so if we go back, the solution to this linear system is right here, because again, this system and this system are equivalent. So sort of some intuition as to what we were doing. We want to use row operations to work this down into an equation with 1 variable, an equation with 2 variables, and an equation with 3 variables. All right. And so notice, since at each stage in this, each of these matrices corresponds to a linear system that is equivalent, right, to the one before it and the one after it, each of these operations is reversible. So I could have alternatively started with this matrix and worked my way to this matrix by just working backwards across these row operations. And so that gives us, so we sort of have a name then for matrices that can be, that you can use one matrix to solve for the other using row operations. And so this is our one definition of the video. We say that 2 matrices are row equivalent if one can be obtained from the other, using the elementary row operations. So using the 3 row operations that we have introduced this video, if you can obtain one matrix from another using some sequence of these row operations, then these matrices are called row equivalent. You might remember that because, remember, these row equivalent matrices correspond to equivalent system of equations. And so as we saw in this example, if two matrices, or we'll say if two augmented matrices, right, corresponding to some system of equations are row equivalent, then their corresponding systems of equations have the same solution set. So, if two matrices are row equivalent, that is if we can use row operations to work one matrix down to the other, I can use this new matrix that I found to find the solution set to the original linear system. Again, it's exactly what we saw in this example, that using matrices in this way and using these elementary row operations, I can find a solution to a linear system that might not be as easy to find just looking at the linear system. And again, some intuition as to how we do that, just sort of getting started with these row operations. Try to work the final equation down to just have one variable and then kind of work your way up. But we'll look at more examples next video and talk about the different types of solution sets we might see.